So we learned about the moment curvature relationship. Now our aim is to find the value of deflection in a slot. So there are different methods that is being developed to find the value of deflection on a slot. So some of the methods is listed here. One is the double integration method, second is the Macaulay method, third is the moment area method, and the conjugate peak method. So in this session we will discuss about the double integration method. Okay. So before moving into the derivation for the double integration method, let us revise the equation. M is equal to EI into d square y by dx square. Right? Now, in our SFT BND, we learned that derivative of the bending moment, right, is going to give you shear force, and derivative of shear force will give you the value of negative of the loading. So if we apply it over here, we can say that shear force F is nothing but dm by dx, which is equal to EI into d cube y by dx cube, and loading W is nothing but df by dx, which is going to be EI into d raised to 4 y by dx raised to 4. Some wonderful relations exist here. So if we rewrite all these things, let us say we have a value of y. Y is the deflection, right? Everything starts with the deflection, the physical phenomenon. And if we differentiate this y with respect to x, it is going to give you the slope. Again, if you differentiate this d square y by dx square and multiply EI, that is going to give you the bending moment. Again, if you differentiate it, it is going to give you the shear force, and again if you differentiate it, we will end up with that. So such kind of beautiful relations can also be arrived at. Okay. Now, what is the reason for this particular relation? So what is the purpose of explaining all these things here? So it's very simple. See, if you have a relation of bending moment, or if you have an equation or a general equation for the bending moment, if you integrate it once, that is going to fetch you the value of slope. Again, if you integrate once more, that is going to fetch you the value of deflection. And that's what's being done in double integration method. Here we are going to do one integration, here the second integration, first integration and second integration. That's what we are going to do here. So the method is called as double integration method. In Macaulay's method also we are following a pattern of double integration method, but it's a modified version. To understand Macaulay's method, we should have an idea about the double integration method. So this is what we are going to do here. So we have derived the moment curvature relationship, and using that moment curvature relationship we are going back to find out the value of slope as well as deflection. Now let us see how the double integration works. So if I consider the equation M is equal to EI into d square y by dx square, and if I integrate this equation 1, what it is going to give you? It is going to give you EI into dy by dx plus c1, right? This is what I am going to get. Again, if I integrate one more time, let us say this is 2, what will happen? Integrate 2, we are going to get it as ei into dy by d, sorry, ei into y plus c1x plus c2, right? We will be left with something like this, and our aim is to find out the value of y. Y is the value of deflection. If our aim is to find the value of slope, we will calculate dy by dx. But to get this value of slope and deflection, we have to find out the value of c1 and c2. They are called as the integration constants. Now the question is, how can we get the value of c1 and c2? The answer is very simple. I think you all are familiar with that. This is a general expression. This can be applied for any beams. But if we want to make this particular equation suitable or suited to a particular question, we have to find the value of c1 and c2 based upon the boundary condition. So, in short, we can say that boundary conditions will give the value of c1, c2. That is the actual method, and that is what we are going to do. So initially we will discuss the double integration method and how it is being applied in the cantilever with an end load W. That is the point of discussion. So if we consider a section here xx, which is located the distance of x from the fixed support, this length is going to be L minus x. This length is going to be L minus x. This is length L. And if I take the moment about x, this is nothing but force into perpendicular distance, which is nothing but, which is the W into L minus x. This is the value we get. Now what we are going to do is, we are going to equate this moment at x to the moment curvature relationship. So we can rewrite it as ei into d square y by dx square equal to w into L minus x. Now there is a small issue here. That issue is nothing but, see, if you apply a law, it is going to bend like this. And this kind of bending is fogging, so we have to impart a negative sign here that is going to come here. Right? Now we will integrate. After equating, we are going to integrate. So upon integrating, we get ei into dy by dx plus c1 equal to, if we integrate w into L minus x, it is going to be w into Lx plus w into x square by 2, right? We'll do one thing. For the time being, I will write the value of c1 on the right hand side. Again, I am integrating it. So what I will get, ei into y equal to minus w into L into x square by 2 plus w into x cube by 3 into 2 plus c1x plus c2, right? This is a general expression. This is a general expression of a cantilever beam, right? Now the question is, how can we suit this equation to find out the slope and deflection? We know that this is going to be the value of slope. This is slope. And this is deflection. To find the value of C1 and C2, we need to define the boundary conditions. Now, what are the boundary conditions we need to substitute? I think you all are familiar with the boundary conditions that we used in columns. Similarly, for this particular beam, we have another set of boundary conditions. So the first boundary condition we are going to substitute it is, at x is equal to 0, here, at this location, what is the value of y? This is the maximum value of y, right? Here the value is 0. So when we use this boundary condition, when we substitute the boundary condition 1, what we will get? Ei into 0 equal to, this term is going to be 0, this is also going to be 0, this is also going to be 0, and finally we get the C2, which gives C2 equal to 0. Right? So that is the first value we got. Now the question is, what should be the second boundary condition? So if we substitute at x is equal to L, y is equal to y max, we are not going to get anything, because we are supposed to find out the value of y max at the end, towards the end. Now if you look here at this particular point, the slope is 0 here at the beginning. So that is a second boundary condition. Say at x is equal to 0, dy by dx is equal to 0. So what we will do, we have an equation here, right? There we will substitute it over here. So the boundary condition 2 gives ei into 0. We are substituting it here, right? This equation is going to fetch is equal to x is 0. So obviously the first term is going to be 0, second term is going to be 0, C1 is also going to be 0, right? So which gives C1 is also equal to 0. So how can we rewrite this equation then? If we use the value of C1 and C2 here, if we use the value of C1, C2 there, how it is going to be? If we rewrite this equation, we can rewrite it as Ei into y equal to minus w L x square divided by 2 plus w x cubed by 6. That is the final value we are going to get. So if we take out the value of w minus w, we can rewrite the equation as L x square by 2 minus x cubed by 6. And if we divide it by Ei, we are going to get it as y is equal to minus w divided by Ei into L x square by 2 minus x cubed by 6. So this is a general expression. Now, if we want to find the maximum deflection which is happening at the end point, we know that maximum deflection is happening at the point y, at the location x is equal to L. So if I substitute that boundary condition, which is another boundary condition, that at x is equal to L we have a y equal to y max. So if I substitute it here, I can say that y max equal to minus w divided by Ei into L cube by 2 minus L cube by 6. Right? So this value is going to be w divided by Ei into L cube by 3. So that is a general expression. So upon rewriting, I can say y max is equal to w L cube divided by 3 Ei. So this equation is a familiar one. You can see this particular equation at many places, but don't get confused. This is an equation that is going to fetch you the maximum deflection value, and this equation will give you the deflection at any locations. You just need to substitute the value of x. So general equation will fetch you any value, even at the end, at the midpoint, anyway. But y max w L cube by 3y is the formulation for the maximum deflection. Similarly, for theta, maximum slope is at theta b. It is nothing but dy by dx. So if I substitute x is equal to L over there, the value I am going to get is w L square divided by 2Ei. You might be wondering why I have neglected the negative sign, because if deflection means it's a distance, right? Displacement. We cannot have a negative displacement. So that's why I neglected the value of w. So these are the equations you should keep in your mind. Okay, so next class I will describe the double integration method for the simply supported beam for a mid-norm. and this cannot be applied to cantilever with the UDL or simply supported. So this is applicable only for cantilever with an end load W. It's very important. You can apply this equation for this system only. This is not a general expression that can be used for any deflection. No, this is only for the cantilever with end load. So we will derive for simply support with mid load, and you can try the derivation for the cantilever with the UDL and simply support with UDL. So in the next class, I will discuss about the double integration method for the simply supported with the mid load. Thank you.